motion graphs. I'm sure you've seen these before, but I need to go over this again. So we have position time, velocity time, and acceleration time. So I'm just going to sketch a sample. We've got a straight line here, horizontal line, and then a curve. So I'm going to break these three up into sections. So here is something moving away from a starting position and increasing its displacement at a constant rate. Here it is, pretend this is a horizontal line. Here it is getting no further or closer from its starting position, so it's essentially stationary. And here it is moving back towards the starting position at a non-constant rate, so a non-linear section here. So how could we sketch a velocity time graph for this motion? Well, going down from displacement to velocity, we consider the gradient m. So velocity is defined as the rate of change of position. So how is this graph changing with time? It's changing at a constant rate. So the velocity here will be constant, and the gradient over this section is positive, so the velocity over this first section is constant and positive. What is the gradient over this section here? That's clearly 0 if we pretend that's a horizontal line. So the velocity along that section where the object is not moving will be 0. And then this final section where it's changing at a non-constant rate. So we're not going to get a straight line like we did for this bit here where it was a straight line. What we're going to get is something moving at an angle. So we start off, that's changing very slowly there, but by the end of this section it's changing very quickly. So that's going to be quite a large velocity there because it's changing very quickly. Here the rate of change is less. The gradient of a tangent to that point would be much less than gradient to a tangent at that point. So the velocity there is small but getting bigger and constant and always negative. So we would have a gradient like that, starting out a little bit negative and becoming very negative. Starting a little bit negative, becoming very negative there. So we looked at the gradient of a position time graph to find a velocity time graph. We could find the instantaneous velocity at any of these points by taking a gradient to a tangent. So instantaneous velocity will be constant through there. Instantaneous velocity through here will be the tangent, the gradient of the tangent to any of those points. There will be equal to the value at any of these points. Acceleration time, again we look at the gradient of a velocity time graph, m. So we look at the gradient of this section here of the velocity time graph, the first section. Gradient of that section is clearly 0, so there's no acceleration there. Gradient of this second section here, again clearly 0, so no acceleration for that part there, moving at a constant speed. So this first section was a constant speed, and constant speed where the speed was 0, so velocity 0, acceleration 0, acceleration 0. This last section, acceleration is the rate of change of velocity, so you can see the velocity is changing here, it's getting more negative, so we look at the gradient of this section. Gradient of this section is constant and negative, so the value of the acceleration there will be constant and negative. So instantaneous velocity is rate of change of position over time. Instantaneous velocity, that would be from a tangent to any one of these points. Average velocity will be final minus initial. So that's again change in x over change in time, but that can be final minus initial over time. The average velocity for this section here, this curvy section, because the velocity is constantly changing. Instantaneous velocity will be a tangent at any of these points. Average velocity will just be the difference between the starting and the finishing position. So the average velocity will be some point in the middle there. Instantaneous acceleration again is a tangent. So you take a tangent to the velocity time graph. Average acceleration, again, still change in velocity over change in time, but this time we can consider final minus initial over time. Going back upwards, looking at an acceleration time graph and calculating the velocity, we look at the area. So the average velocity for this section here would be the area here. And so too, finding total displacement from velocity time graph. If you were given a velocity time graph like this and asked to work out how far this object had travelled, you would calculate this area in here as displacement in the positive direction because it's above the x-axis. So this area under the velocity time, this section of the velocity time graph indicates displacement in a positive direction. This area under here indicates motion in a negative direction, so it's displacement back towards the starting point, so displacement in a negative direction, motion in a negative direction. You can see from this top graph of displacement that the object moves away from the starting point and then returns back to that same position 0 here. So that tells us that this area is equal to this area. So going down from position to velocity, from velocity to acceleration, consider the gradient. Going upwards, consider the area. One last thing, centre of mass. When we consider motion of complex objects, we consider it really just the centre of mass. Here's me holding a hammer, and you can see I'm balancing it on my fingers, sort of, with the centre of mass being there. So that's sort of the balance point of an object. So rather than drawing complicated physics diagrams, we tend to just draw single point diagrams to represent an object. We draw those points as the centre of mass. Good little video here, I'll show you in class, but you may like to look that one up, an MIT physics demo. Okay, that's all for this one.